Hello, chemists. This is Ms. Placino, and you're watching lesson 9.6 on entropy. In today's lesson, we're going to talk about what role disorder plays in a chemical reaction. I think entropy is kind of a fun and interesting topic to think about, and it's really cool to see how it plays into the spontaneity of a chemical reaction. I'm getting a little ahead of myself, so let's talk about some goals for today's lesson. You should be able to explain what entropy is. You should understand what positive and negative changes in entropy mean. And really, the big one for today, you should be able to predict the entropy change of a system. Namely, is it increasing or decreasing, basically by looking at like before and after pictures of the system. We're going to look at both chemical and physical changes today, and we're going to keep things very qualitative. So what I mean by that is we're going to keep numbers out of it. We're just going to kind of describe has entropy increased or decreased in a given situation. All right, let's get started. Entropy is addressed in the second law of thermodynamics. In the description below, there's a link to another video that has a fun, maybe 5 or 6 minute lesson on the second law of thermodynamics and entropy in general. I would really recommend pausing this video, go check that one out, and then come on back and wrap up with the lesson. My guess is you've experienced the second law of thermodynamics in your own life. Say you've got your bedroom. Guess this kind of looks like a dorm room. Everything is pretty neat and organized. This is probably what your parents want your room to look like, where everything has its place. Have you ever had to clean up your room before? I'm sure you have. How long does it take? Yeah, some of you probably it's never happened, so you have no idea. Maybe other people can do it pretty quickly. Maybe you shove everything under your bed or in a closet. But if you really do an honest-to-goodness cleaning and organizing of your room, chances are it takes a pretty hefty amount of time. It seems like almost on its own, without even trying, your room probably ends up looking like this, where there's just a mess everywhere, your bed's unmade, maybe there's food in your room, just nothing is really where it belongs. How long does it take your room to get messy? Yeah, it probably happens almost instantaneously. I know I get home from school, I take off my jacket, my shoes, I put my bag down, I make a snack, and before I know it, it looks like my kitchen has exploded. There's a natural tendency for a system to become more disordered. If I want to take my messy room or my messy kitchen and turn it back into my highly organized, neat room, it's going to require effort or energy to do so. This is effectively the second law of thermodynamics. The disorder of the universe is always increasing. So we're able to go from neat to messy pretty much without doing anything in particular. Things get disorganized on their own. And if we want to get back to a highly organized system, it's going to require energy. So here we have a little cartoon. We've got, looks like a mom character constantly asking what's happening, how did this mess happen? And we've got the kid just saying entropy. This is the natural tendency of the world. Everything is moving to a state of disorder and kind of chaos. Entropy has the symbol S in thermodynamics. And entropy is really just a measure of the degree of randomness of the particles in a system. So something like a gas where your particles are in constant movement, there's really no order whatsoever, that has a very high entropy. Something like a solid, where the particles are in more of a fixed, rigid location and maybe just vibrating a little bit in place, has a comparatively speaking low entropy. Again, we're going to keep numbers out of it for the time being. When we go to evaluate entropy, we really want to think about what's happening to the degree of disorganization or the messiness of the molecules as you move from reactants to products, or if it's a physical change, from initial to final states. We talked about enthalpy in the last couple of lessons, and we know that the sign of delta H is extremely important, and we've got information kind of coded into it, whether a system is exo or endothermic. The same thing applies to entropy. The sign is extremely important. If you move to a system where the reactants are less disorganized, you have a negative delta S, or a negative change in entropy. If in your system the products or the final materials are more disorganized, they've gotten messier, you have a positive delta S. A positive delta S is what we call energetically favorable, basically meaning that energy is released. Systems in nature tend to move towards a more low energy state. If we kind of think back about enthalpy for just a moment, what would be more energetically favorable, an exothermic or an endothermic reaction? Hopefully you're thinking exothermic. Exothermic reactions by definition release heat or energy into the environment, lowering the overall energy of the system. All right, so before we move on the next page, you've got, I think, like 7 or so pictures of changes in enthalpy. So we'll play like kind of a very brief chemistry Pictionary. What I'd like you to do is look at those pictures and try to figure out what factor affecting entropy we're going to talk about. And if you're able to brainstorm a little bit about, how, changing that condition or changing that factor will impact entropy, feel free to jot that down as well. So pause the video, try that out, and we'll get started again when you're ready. All right, so hopefully you kind of identified what you think those pictures are talking about. Here's our first one. Hopefully this is a pretty easy one. We're looking at phases and entropy. Of course, we have a solid, a liquid, and a gas, our 3 traditional phases of matter. Any change that leads to the creation of a gas is going to increase the entropy of a system. So whether it is a simple physical change going from liquid to gas, boiling, that represents an increase of entropy, or if we have some sort of chemical reaction where we take a solid as a reactant and we produce gases as a product, that is also an increase in entropy. So if you've got a chemical reaction and you have phases included, if you've got to figure out which has more entropy, it's really a matter of looking at which side has more moles of gas. The side with the more moles of gas is going to have the greater entropy. All right, picture number 2. What are we trying to show here? This is the formation of a mixture. So mixtures and entropy. Anytime you create a mixture, and just to remind you, a mixture is physically combining 2 or more pure substances, you're going to experience an increase in entropy. So we have, looks like an element here, another element here, and now we have a mixture of elements. There is more randomization in our mixture than there is in either of those just 2 pure substances. So anytime you create a mixture, you will increase entropy. The most common form of this is taking like a solid and dissolving it in a liquid to form an aqueous solution. All right, picture number 3. Yeah, temperature changes and entropy. How might temperature impact the entropy of a system? Faster particles move more randomly, so entropy increases as temperature increases. We see this direct relationship. So let's say you have a sample of water at 20 degrees Celsius, kind of room temperature, what's coming out of the tap, and you've got a sample of water at 80 degrees Celsius. The higher the temperature, the more movement those particles are going to have, and the greater chance for them just to be distributed randomly and have random movement. So as temperature increases, entropy increases as well. What do you think we're trying to show in this picture? Particles of a gas. We're compressing them in a cylinder. Yeah, this is pressure and entropy. Which of those 2 systems has more entropy? Canister 1 or canister 2? Hopefully you're thinking canister 1. Those particles have a whole lot more room to move around in canister 1, so there are just more ways to arrange them, more random organization. In canister 2, there's less room to move around, so the particles are not going to be able to spread out as much. You have fewer possible ways to organize them. So when pressure increases, there is just less space for the particles to move, and as a result, we see a decrease in entropy. So we've got this indirect or inverse relationship. Pressure goes up, entropy goes down. This one is kind of tough. You might have been able to get the ones before it. This is quantity and entropy. So just really amount of stuff and entropy. Sometimes you'll be given something like a chemical equation, phases are missing. You don't kind of just intuitively know. Like for example, if you see O2, you know the overwhelming majority of the time that sample is a gas. Let's say you got a bunch of substances that you're just really not familiar with. In kind of a last resort situation, you can look at number of moles of particles. The more moles of particles that are present means that there are more ways to arrange them. So entropy tends to increase with quantity. So the side of the chemical reaction that has a greater number of moles is going to be the one that is more entropic. Again, this is really a last resort. This is not the first thing you should turn to. You can kind of just like go down the list in the order that they've shown up for these different factors affecting entropy. And if you can't do it with things like making a mixture, moles of gas, temperature, pressure, etc., then and only then should you kind of resort to quantity to predict entropy. All right, what might we be talking about here? Kind of looking at size and entropy here. So we have a atom with 2 protons and 2 neutrons. That sounds like helium. And other atom has 36 protons. That's going to be krypton. So let's say you've got these 2 samples, helium and krypton. They're both gases. Let's say they're at the same temperature, they're at the same pressure, there's the same quantity. We'll say like a mole of each just for the sake of argument. If I've really got to try to gauge which of those samples would be more entropic, I'm kind of left just looking at size. Larger molecules and atoms tend to have greater entropy than smaller ones. In the case of an atom, you will know that these electrons are in constant motion, so they're just more particles moving around, so we should see a higher degree of entropy in an atom of krypton than we would for an atom of helium. Same deal with greater molecules. We tend to think of molecules as being these fixed, rigid objects, but in reality, those bonds are bending, they're vibrating, they're stretching and flexing. So larger molecules will tend to have a greater entropy than smaller ones if they're the same phase and under the same temperature and pressure conditions. So that's, again, kind of a not quite last resort, but if it's really difficult to try to gauge and you can't use things like, phase of matter, temperature and pressure conditions, you can use size to make an educated guess on entropy. All right, you've got some practice problems in your workbook to really just kind of work on identifying which system would be more entropic and providing some explanations as to why. Definitely take some time to hammer home the basics on this concept. We're going to be making things a little more quantitative in lesson 9.7. All right, good job today, chemists. Thanks for tuning in, and I hope you found this helpful.